What's up? I'm Vin, and today I want to talk about the different types of discontinuities. So these are the two examples we're going to go through. Here are some notes that'll help us with these questions, and let's get started. So for question 1, the first thing we want to do is find the domain and the zeros of f of x. Well, when we're looking for the domain of a function, we're trying to find out if there are any values of x that would make the function undefined. So one thing we could look for is zeros in the denominator of this function. So since our denominator is 9 minus x squared, the only restriction we have right now is that 9 minus x squared is not allowed to equal 0. Other things to look out for are square roots or fourth roots, even roots of negative numbers, but in this case we're just setting our denominator equal to 0. So when we solve this out, 9 minus x squared is equal to 0 when x equals plus or minus 3. So then our domain is all values of x, all real numbers except x is not allowed to equal plus or minus 3. So this answers the first part of A. But now to look for the zeros of f of x, you have to think about this very carefully. Since our function is in the form of a fraction is equal to 0 when the numerator is equal to 0 and the denominator is non-zero. So you just have to be very careful here, because when we set the numerator equal to 0, we have absolute value x times x minus 3. We're setting that equal to 0. We're going to get two roots at first. We're going to get x equals 0, and we're also going to get x equals 3. However, if we just rush forward to part B, we're going to walk into a very dangerous trap here. We have to reject x equals 3 because x equals 3 is not in the domain of the function. If you were to plug x equals 3 in, it's going to make both the numerator and denominator equal to 0. So this tells us that we only have one root, and our one root is at x equals 0. Now for part B, we want to investigate, well, what happens at x equals 3? What is the limit as x approaches 3 of f of x? So to do this, we can't evaluate this limit by direct substitution, because once again, when you plug in 3, you're going to get 0 over 0, which with limits, that's an indeterminate form. So what we do is we take the original function, but we factor the denominator, which is the difference of two squares. So we could write this as 3 plus x times 3 minus x. And if you look here, these factors can cancel, x minus 3 and 3 minus x, but there's going to be a leftover of negative 1. So then this limit is going to work out to the limit as x approaches 3, and we have negative 1 times absolute value x. We could just write that as negative absolute value x over 3 plus x. And then when we simplify this, now we could substitute, because we're going to have negative absolute value 3 over 3 plus 3. But just be a little careful here. The negative is on the outside, not the inside. So the numerator is going to simplify to negative 3 over 3 plus 3. So we're going to have negative 3 over 6, which equals negative 1/2. So for part B, we get an actual value here. Our limit as x approaches 3 is equal to negative 1/2. Now for part C, this is a little bit more involved. The easier one to solve is for the vertical asymptote. It's just a little bit less work to do. And the steps for finding vertical asymptotes are that you have to take your function, you have to factor it completely, you have to cancel common factors, and then set the leftover factors in the denominator equal to 0. And notice we already did a lot of that work in part B. When we factored this completely and canceled, the only factor left in the denominator is 3 plus x. So if we set this equal to 0, this tells us that our only vertical asymptote occurs at x equals negative 3. So we already have part of our answer for part C. But now for the horizontal asymptote, there's a little bit more to do, and there's a little bit more concepts mixed in here. To find the horizontal asymptotes, you just have to look for the limit as x approaches plus or minus infinity. So we have to evaluate two limits here. And we're finding the limit of f of x as x approaches plus or minus infinity. So we write this out here, but in my experience, the part that students will struggle with the most is the absolute value component. So what you want to think about when you're doing limits of absolute value is you have to think about, for one, the piecewise definition of absolute value, that it's equal to x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0. So when we're finding the limit as x goes to plus infinity, that's a situation when we're at x greater than 0 And in this case, the absolute value of x is just equal to x. So when we evaluate this limit, this is now the limit as x goes to infinity. And absolute value x we could just replace with x because we're on the positive side of 0. So we have x times x minus 3 over 9 minus x squared. So when we expand the numerator, we distribute in the parentheses, we're going to have x squared minus 3x. And I'll write the denominator as negative x squared plus 9. Because then we just have to focus in here on the leading terms. If we focus here on x squared and negative x squared, and we're only allowed to do this because it's a limit as x approaches positive infinity, and we have a rational function left here, that we just look at the ratio of the coefficients. Notice we have matching degrees. It's degree 2 on top and bottom. So we're just doing the limit is equal to 1 over negative 1. So the limit is just equal to negative 1. And we're going to write our final answer out in a little bit. But this means we have so far one horizontal asymptote, the line y equals negative 1. But then to see if we have a second one, we also have to investigate what is the limit as x approaches negative infinity of f of x. So we just write out everything again like we had it before, except this time around the thought process is a little bit different. And this is the one that I would say students will struggle with the most. When x approaches negative infinity, that's when you're at x less than 0, and absolute value of x is equal to minus x. So we're only going to be replacing this absolute value x here, except this time around we are replacing it with a minus x. So then this limit, when we work this out, is now the limit as x approaches negative infinity, and we're going to have negative x squared plus 3x this time around over negative x squared plus 9. So when we evaluate this limit, it's negative 1 divided by negative 1, which gives you a positive 1. So our horizontal asymptotes, we have two of them, y equals plus or minus 1. Are the horizontal asymptotes. Okay, for part D, what we want to do is we want to classify the discontinuities of f of x as either a jump, removable, or infinite discontinuity. So we're going to use our work for part A, B, and C here, along with these notes. In part A, we said that the domain is all real numbers except x can't be plus or minus 3. So let's take a look at what do we have at x equals 3. So f of x has what type of discontinuity at x equals 3? Well, if we look at the work for part B, we found that we actually have a limit as x approaches 3 of negative 1/2. So if you take a moment to read through these, you'll see that we have a removable discontinuity at x equals 3 because the function has a limit, it's just not defined there. So the limit is not equal to the function value because there is no defined function value at x equals 3. Okay, now to answer the rest of this question, we also have to classify what type of discontinuity do we have at x equals negative 3 now. And if we look here, we said in part C that we have a vertical asymptote at x equals negative 3. And out of all of these discontinuities here, the vertical asymptote indicates that you have an infinite discontinuity, because if your function is going up to plus or minus infinity on either side, that means that you have an infinite discontinuity. Okay, so let's take a look at a graph of the function of f of x. So to type in this fraction, we have alpha y equals enter. And we're looking at absolute value x. So we press math, scroll over to number, and option 1, ABS, is for absolute value. So we type in our x, and then next to x, we have parentheses x minus 3. And in our denominator, we have 9 minus x squared. So if we press zoom 6, this is going to give us a standard picture here of what our graph looks like. Now we're going to grab this and bring it back to our workspace to analyze and see if our answers check out. For part A, we have the domain is all real numbers x except plus or minus 3. Well, at negative 3 here, we have a vertical asymptote. So it's pretty obvious just by looking at the graph here that the function is undefined at negative 3. So the graph does support part of our answer. At x equals 3, things are not as obvious, but if we look at the table alongside the graph, we'll see that there's an error at x equals 3, which means that this graph is going to have a hole in it at x equals 3, which also supports that we have a removable discontinuity at x equals 3. Now for part B, we said that the limit as x approaches 3 is equal to -1/2. We could see here that at this line, that's -1. So -1/2 is in this space here. So if we look, the limit as x approaches 3 from the left side and right side is heading towards -1/2. So since our limit is also supported by the graph, we could be sure that our answer to part B is also good. Now in part C, we found that we have horizontal asymptotes at y equals plus n minus 1. So if we draw a horizontal line through +1, we're going to see that this portion of the graph in quadrant 2 does have a horizontal asymptote of y equals 1. And if we look at y equals -1, heading in this direction here in quadrant 4, the other portion of the function here in quadrant 4 does have a horizontal asymptote of y equals -1, so that is also supported. And we already said before, we have a vertical asymptote at x equals -3, which is seen on this portion of the graph here. Now the last thing to mention is that we have an infinite discontinuity at x equals -3, and notice we have our vertical asymptote here, so we have a left side limit at -3 going to positive infinity, and on the right side of -3, our limit is going down towards -infinity. So we definitely have an infinite discontinuity there. Now we have a removable discontinuity at x equals 3 because we have a limit as x approaches 3. We are heading towards a y value of -1/2, but because the function is undefined at 3, that means we have a removable discontinuity. Okay, for question 2, we're starting off here looking for the domain of g of x. And one thing that'll help us here to find the domain is to rewrite g of x in an alternate form, so then it's more obvious which values of x are going to be restricted. Now, one thing to note here is that a represents a positive real number. So when we rewrite this, we have a to the negative first power, we could call 1 over a. And minus x to the negative first power, we could write as 1 over x. And this whole term here in parentheses is raised to the negative first. So then I could rewrite this whole thing as 1 over, and we have 1 over a minus 1 over x. So when we're identifying the domain of g of x, a few things to pay attention to are values of x that are going to make this entire expression here in this fraction undefined. So one that jumps out right away is if x is equal to 0, we're going to have 1 over 0 in this piece here, which is a problem. So 0 is not allowed here. Now another one that's not as obvious is when the entire denominator, when 1 over a minus 1 over x is equal to 0. This is also a problem for us, and this is going to be true when x is equal to a. Then you're going to have 1 over a minus 1 over a equals 0. So the domain is all real numbers except 0 and a, where once again a is a positive real number. So we found the domain, but now we want to find the zeros of this function. But to do that, remember what we said before. The fraction is equal to 0 when the numerator is equal to 0 and the denominator is non-zero. But at first glance, you'll look at this and say, 1 is never going to equal 0, so I'm not going to have any roots. But just to be very convinced of this, what we could do is we could multiply the numerator and denominator by ax. And what this tells us is that we could express g of x as ax over, and if we multiply ax times 1 over a, we're going to have x. And then we have minus 1 over x times ax is just a. So this is an alternate form of how we could write g of x that's going to make it a little bit easier to answer the rest of part A and also answer the other parts. And if we look here, the goal was once again to find the roots or the zeros of g of x. So if we set ax equal to 0, remember a is a positive real number, so this tells us that x would have to equal 0, but we're going to reject this. And why are we rejecting this? Well, 0 is not in the domain of the function. So that means that this function has no roots. So for our answer to part A, here's our domain. And we also have no roots for this particular function. Now, the next thing that we have to do here is find the asymptotes of g of x. So to do this, remember for the vertical asymptotes, what you want to do is you want to factor. You want to cancel out common factors and then set the leftover factors in the denominator equal to 0. Well, notice this has been factored completely. So we could set the factor in the denominator x minus a equal to 0, and this tells us that we have a vertical asymptote at x equals a. So right away, like, we're done with finding our vertical asymptote. We just have one of them. Now for the horizontal asymptotes, this is a little bit more involved, but remember, we're finding the limit as x goes to infinity of our function g of x. But it's better to write g of x in this form, ax over x minus a. That's why this algebra is pretty useful for answering the rest of the question. And if we look here, ax over x, we have leading terms, ax and x. So when we want to find the limit as x goes to infinity, we're just going to compare the ratio of their coefficients. So we're doing a divided by 1, which is just equal to a. So far we have a horizontal asymptote of y is equal to a. But just to be safe, we're also going to check the limit as x goes to negative infinity. But notice here, when we evaluate this limit, it's the same process. If we use our rational function theorem, there's no special name for it, but the conclusion of this theorem says that when you have a rational function going to infinity or negative infinity, that you really just have to look at the leading terms. So these are the only terms I'm looking at when I'm evaluating my limit, and the x over x is going to cancel for this limit, and my limit is equal to a. So I'm not going to write y equals a second time, but the fact that our limit worked out to the same thing at plus n minus infinity tells us we just have one horizontal asymptote of y equals a. So for part C, we just want to evaluate these three limits. And the first limit is not too bad. This one we could evaluate by direct substitution. We have the limit as x approaches 0 of g of x, and we want to use this representation from before, the ax over x minus a representation, because this is going to be easier to deal with. And the first thing you should try with limits is plugging in. So we're going to have a times 0 divided by 0 minus a, which is going to be equal to 0 over negative a. And remember, from before, we're assuming that a is a positive real number. So this just works out to 0, and we have our first limit done. For the second limit, we have the limit as x approaches infinity of g of x, which once again, we're using ax over x minus a. And we did this before when we found the horizontal asymptotes. All we have to look at is the ratio of the coefficients of x in the numerator and denominator. And this is just going to be a over 1, which is just equal to a. So once again, the first two limits are not so bad, but the third one you have to be very careful with. The third one is definitely a bit tricky. So for this one, we're looking for what is the limit as x approaches a of g of x, which is once again ax over x minus a. And for this one, we're actually going to have to investigate limits on the left side and right side. We'll start with the right side first. We're doing the limit as x approaches a from the right side of ax over x minus a. And what makes this limit a little bit more challenging than the others is that you really have to do most of the work in your head. So it's really about how you think about this that makes it easy or makes it more challenging. So how you want to approach this is when you think about the number a is once again a positive real number. So we could just say it's here on the number line. So if I'm plugging in a number to the right of a, because we're approaching a from the right side, that means I'm thinking about a number around here. So when I do a times a, I'm going to have a squared. And I know that this is going to be something positive in the numerator. But now be very careful with how we think about the term in the denominator. We're going to have a number to the right of a minus a, which is going to result in a small positive number, which will represent that with 0 plus here. This means a small positive number, a number slightly to the right of 0. And when you think about what happens to this quotient when I divide a positive number in the numerator by a tiny positive number in the denominator, well, this is going to trend to positive infinity. So this first limit that we're looking at here is heading towards positive infinity. But now we also have to investigate what's happening on the left side. What happens as we approach a from the left, and we're still focusing on g of x here. Well, now when we think about the left side of a, then when we're going back to this number line here, here's a again, but now we're on this side. So when we do a times a, we're still going to have a squared. And this is still going to be a positive number because a is a positive real number. So to the left and right of it, when we're very, very close, is also going to be positive. So no problems with the numerator, but the denominator is where things get tricky. Now you have a number less than a minus a, which is going to work out to a very, very small negative number. And remember, the idea is that we're getting infinitely closer to a. So that space is just getting smaller and smaller. So this is going to become a tiny, tiny, tiny negative number. So now I have a positive number divided by a super, super, super small negative number, and that's going to head towards negative infinity. Okay, the most common mistake I see with this is people think this is an indeterminate form, but anytime you have a number divided by a small positive or a small negative, you can say whether or not it's going to plus or minus infinity. So this limit heads towards negative infinity, but remember, with limits, when the right and left side limits are not equal, that tells us that the limit in general does not exist. So this limit here, as x approaches a of g of x, does not exist. So for this last part here, we're going to classify the discontinuities of g of x, and we're going to use our work from part A and part C to answer this. So in part A, we said that the function is undefined at x equals 0 and x equals a. So when we investigate these limits, in part C, we said the limit as x approaches 0 of g of x is equal to 0. So since the function has a limit at x equals 0, but the limit is not equal to the function value at x equals 0, that means we have a removable discontinuity at x equals 0. Then the last thing that we need to classify here is what type of discontinuity do we have at x equals a? Well, if we notice, the limit as x approaches a from the left side goes to negative infinity, and the limit as x approaches a from the right side goes to positive infinity, which tells us that we have an infinite discontinuity at x equals a. Okay, well, this is going to conclude this video. If you found this video to be helpful, please click the like and subscribe buttons below. It really helps me grow the channel. And if you got any requests, topics you want me to cover in the future, just leave them in the comments section below. And thank you for watching.